So, now magnetic dipole in uniform magnetic field. Suppose you have got uniform magnetic field like this is here, this is B, and we are placing magnetic bar magnet like this, where is the north is here, south is here, and this is angle is here theta, length is 2L. So, when this bar magnet is placed in uniform magnetic field, it experiences here torque, and that torque can be given is here, that is m cross B, that is called mb sin theta. So, this is about here the torque, magnitude of the torque. So, in this case the torque is here, and when this magnetic dipole or this bar magnet is suppose rotated by a small angle here, and then we can calculate the work done against this magnetic torque. So, we can take here, suppose if you are rotating this bar magnet by a small angle d theta, then you can write here dw is equal to torque into d theta, and then you can write dw is equal to mb sin theta d theta, and then we can take the total work done, dw is equal to mb sin theta. Here we can write theta 1 to theta 2, that is a d theta. So, we can write mb minus cos theta, and here theta 1 to theta 2. So, now we can solve it here, that is upper limit minus lower limit, and we will be getting in this case w is equal to mb, and it is here minus cos theta 2 plus cos theta 1, and that can be written mb cos theta 1 minus cos theta 2. This is the work done in rotating the magnet from angle theta 1 to theta 2. If you are taking suppose theta 1 is equal to 90 degree and theta 2 is equal to theta, then you can write w is equal to, here this is 90, that is 0, minus mb cos theta. For this symbol we can give u, that is the potential energy of the magnet, and this is minus mb cos theta. If theta is 0 here, which is the angle between magnetic field and magnetic dipole moment, if theta is 0, potential energy will be minimum, and the magnet which is here, it is suppose left after displacing by a small angle, it will oscillate and comes back to the original position. That means it will align along the magnetic field. In this case theta equal to 0, potential energy is minimum, and that is called stable equilibrium. If you are taking theta is equal to 180 degree, cos 180 is minus 1, that will become plus mb. The potential energy is maximum, and that is called condition for the unstable equilibrium. So, now see here, if the bar magnet is suppose displaced by a small angle and left free, then it oscillates for some time, and we can calculate the time period of the oscillation of this. So, now let us discuss the time period of the oscillation of the bar magnet. So, suppose bar magnet is displaced by a small angle theta, then we can write here, in that case torque acting on the magnet is torque is equal to, that is here can be written m cross b, and that can be written mb sin theta, where m is magnetic dipole moment. This torque is known as restoring torque here, and also the torque applied external torque is equal to I into alpha. So, we can write here I alpha is equal to, in equilibrium here, that is minus mb sin theta, and we can write I is a moment of inertia, not current here, d square theta upon dt square, and is equal to minus mb theta, where we have taken sin theta is approximately equal to theta for small angle. So, we can write here d square theta upon dt square plus mb upon I theta is equal to 0. This equation we can compare with the equation for the simple harmonic motion, that is a angular simple harmonic motion. Then we can write here this one is equal to omega square. So, omega square is equal to mb upon I. So, omega is equal to under root of mb upon I. This is here 2 pi upon t is equal to under root of mb upon I. And now here we can get the formula for time period. T is equal to 2 pi under root of I upon mb. So, this is the time period of the magnet or the needle, magnetic needle, which is oscillating in uniform magnetic field.